Okay, so for this problem, you're kind of working with Kirchhoff's loop rule, and I'm going to go ahead and use the sort of loop method that MIT professor Walter Lewin uses, because the one that the textbook uses sucks, and you get like 15 million variables. So the way that you do this is basically instead of defining like a new current at each junction, like so, maybe this is like I1 splits off into like I2 and I3. You don't really do this because you get a lot of currents. You get like in this problem up to 6. And working with an equation or working with a system of 6 equations kind of blows, especially on a test. So what I like to do instead is basically you define a current for each loop. So for example, say in this one we have a current going in this direction, right? And the direction you assign it is arbitrary. It could be like this, or it could be like this. It could be going clockwise or counterclockwise, essentially. We'll go over how to handle that later if you get the wrong one after arbitrarily assigning it, but it kind of handles itself, so it's no big deal. So yeah, we're going to go ahead and do this for all of the loops here. This is, I'll call it I2, and this one I'll call it I3. So the big idea here is, well, every time we pass through a current, say looking at current at the 15 ohm resistor, right? We have I2 going down and I3 going up. Well, when we have opposing currents, the current through each resistor is going to be the difference in the currents. It's going to be I2 minus I3, or maybe I3 minus I2. Which one of the two, I'll let you know in a second, but we can't determine that at this instant. So, right, the current through a resistor is basically if you're going to get the difference, or maybe the sum if they're going in the same direction, like this. That would be I2 plus I3, no matter how you think about it, because the currents are going in the same direction. So they add up. Now, for the voltage source at the bottom, I basically, in this case, the direction does kind of matter, because if you approach a, say this is, again, the 6-volt resistor, if you approach a current from the negative to the positive terminal, then you gain voltage, you gain 6 volts. However, if you go opposing a battery, like this, you're essentially charging it, and you actually lose 6 volts. So the direction does matter, but in this case, we're going in the direction of from negative to positive, or from, yeah, we're going from negative to positive, so we gain voltage. Now all we got to do here is basically create an equation using Kirchhoff's loop rule, where basically going through any loop will result in a voltage change of 0, no matter how you, no matter what path you take. So we're basically going to go through each loop variable that we've defined and create an equation off of it. So for example, the I1 loop, starting from this little vertex, we're going to pass through the 6-volt battery. And we're going from negative to positive, so we gain 6 volts, right? We do 0 equals plus 6 volts. Now from here, we reach the 25 ohm resistor. Now the 25 ohm resistor, it has I1 going down it, right? I1 is going here, but I2 is opposing it. So the total current passing through this resistor in the perspective of I1 will be I1 minus I2. In this case, because we're considering it in the perspective of I1. So no matter what, I2 is going to be going against I1. It's more abstract than it is like, yeah, it's more of a directional thing. So we always drop voltage when we pass through a resistor. So minus 25 ohms times I1 minus I2. And then after that, we're going to pass through the 14 ohm resistor. And again, looking at the 14 ohm resistor, I3 is opposing I1. I1 is going in this direction, and I3 is going down. So the current passing through that 14 ohm resistor is going to be I1 minus I3. And then from there, we just wrap around back to our vertex as follows. Right, we could just go back here all the way down to where we started from and complete our equation. So this should be I3. Right, the big idea here is basically we can create an equation for each loop variable that we define. So you get a one-to-one correspondence in the number of equations and the number of variables. And it ends up being nicer than the textbook method because you end up with less variables and equations in general. So yeah, that's a general approach for this problem. This should be like way over here, but whatever. Okay, now for the I2 loop, say I start from, I don't know, any vertex, this one. I'm going to pass through the 22 ohm resistor. Now the 22 ohm resistor, you can see that it only has I2 acting on it. There's no current going with or against I2. So the voltage going through it is, the current going through it is just I2. So minus 22 I2. Then we reach the 15 ohm resistor, and as you can see here, I'll go ahead and use red. The two currents are opposing. I3 is going in the opposite direction of I2, so the current going through it is going to be I2 minus I3, right? Now once again we go through here, and so the 25 ohm resistor, like last time, we realized that the I1 and I2 currents are opposing it, right? I2 is going in this direction, whereas I1 is going in this direction. However, in this case, just make note that we're in the perspective of I2, like we're following the I2 route. So what we'd write here is I2 minus I1, as opposed to I1 minus I2. Again, it's just a difference in perspective, and it's to show that this shows that I2 is taking from I1, but this one shows that I1 is taking from I2. It's mostly a perspective thing, but it does matter in your equations. So, right. Now we just do an equation for I3. Again, we can start at whatever vertex we want, say this one up here. And again, passing through the 12 ohm resistor, the only current that acts on it is I3. So the current there is just going to be I3. So 0 equals opposite 12 I3. And you always subtract when you're dealing with a voltage drop from a resistor, because that's all resistors do. They drop voltage. Okay, and now we see here that in the 14 ohm resistor, it's going to be I3 down and I1 opposing. So the current going through the 14 ohm resistor is I3 minus I1. And now at last we reach the 15 ohm resistor, which again I2 is opposing. So minus 15 I3 minus I2. So now we have these three equations. They're a bit bundled up weirdly, but that's just because, let me fix that really quickly. This should be like this. Like this. Oops. And, alright, so here we have like our three equations. And again, we're only dealing with three equations because we're using this method instead of like the create a new variable at every branch, which can lead up to 6 equations in this problem. So, this parentheses should be here, but whatever. Point still stands. We can create an equation for each loop variable that we define, so the system is complete. And I could show you the algebra behind it, but I'm just going to go ahead and show you a quick system of equation solver here on my virtual Nspire. And we get that I1 is equal to 0.330324 amps. I2 equals 0.176068 amps. And I3, I3 equals 0.177209 amps. Okay, so now that we have the individual loop currents, if we wanted to find the current through each resistor, we'd basically have to just imagine soloing it out. So the first one they asked for is the 12 ohm resistor. Now the 12 ohm resistor, again, the only current passing through it is I3, right? So for this one, I of right here, I of 12 ohms. Actually, let me do it all the way up here. I of 12 ohms is just I2, which is equal to, or not I2, I3, and that's just equal to roughly 0.18 amps. Now, for the next one they asked for is the 14 ohm resistor. And looking at the 14 ohm resistor, we realized this was one of those that had opposing currents, right? We had I3 going this way and I1 going up. So, right, we have our 14 ohm resistor, and we have a roughly a 0.33 amp resistor, or amp current, that's I1, and a roughly 0.18 amp current going down. So basically, to determine what the final current would be, think about it as like almost like forces. It's like the net force or the net current that's going through here. In this case, 0.33 is going to be the stronger of the two currents, right? It's going to be the larger value. That's basically what matters. So that sort of determines the direction. We're basically going this way, and we're taking out 0.18 amps this way. So it's so our current through here is going to be I1 minus I3. If we do I3 minus I1, we're essentially considering it from the perspective of I3. So basically we're saying, oh, the current goes down. But then we're going to get a negative value, which corrects itself and tells us that we're going up, right? And actually, I'd like to backtrack here for a second because I forgot to make note of this. But when we're solving for our currents in our final system of equations, say that I1 is negative, right? We get a negative value for one of our currents. Well, all that means is that, remember the arbitrary direction that we assigned? We basically made all of these clockwise, which happen to be correct. Well, if we get a negative value, that just means that it's actually going the opposite direction. So it's going counterclockwise for I1, for example. And we could just simply account for that. Our equations already account for that, and all we have to do is take into consideration when getting the individual currents. So we just sort of make a little annotation, correcting ourselves, like, oh, we're actually going back. And then, that basically takes care of itself. But in this case, our initial assumption happens to be completely right, which is nice. So, right, going back to here, the current through this resistor would be I1 up and I3 down. However, I1 is the larger current value, so it dominates, and the net current is going to be going up. So it's going to be I1 minus I3, and that's going to be roughly, where is that? That's going to be roughly 0.15 amps. I'm going to go ahead and get rid of the equations. They're taking up a lot of space, and we're kind of past that section now. Now, the 15 ohm resistor, and this one they asked for the direction specifically in part B. So the 15 ohm resistor looks like we have, sort of looking at it on our diagram, it's I3 going up and I2 going down, right? So we're looking at this right here. You can sort of see that the arrows are in opposing directions. So of the two, we sort of have to consider which one's the dominant current, which one sort of determines the direction. Well, I3 is just larger than I2, 0.177 versus 0.176. So the net current is going to be going upwards. So first of all, that's part B, right? Part B should be upward. And if it's going upward, or if I3 is the dominating one, then I2 is sort of the current that's taking away. So to get the actual calculation will be I3 minus I2 as opposed to I2 minus I3. And that gets us roughly 0.0011 amps, a very small current because the two values are close. Now for the 22 ohm resistor, I22, we'll go ahead and take a look at it, and hey, it's one of the nicer ones. It only has I2 going through it, right? So this is just equal to I2, and that's going to be roughly 0.18 amps. I'm rounding to two significant figures because that's what the problem wants us to do. And I25, the current through the 25 ohm resistor, again, we see that I1 is going down, but I2 is going up. So we have to consider which one's sort of dominant current, I1 or I2. And in this case, it's going to be I1, right? 0.33 versus 0.17. So the net current is going to be I1 minus I2, and that's roughly 0.15 amps. So right, to sort of summarize, basically, Kirchhoff's loop rule introduces this new idea that you can have opposing currents in two adjacent loops, and that sort of defines the individual current through each component. Sort of if the two currents are going together in the same direction as follows, say I1 and I2 in some random circuit. In this case, the current going through that resistor is I1 plus I2. Or if they're opposing currents from adjacent loops, then it's either going to be I1 minus I2 or I2 minus I1, depending on which perspective you look at it, depending on which loop you follow. So yeah, that completes the homework number 3.